Dear students, today in this video lecture we are going to discuss electric dipole in a uniform two-dimensional electric field. So you can see the diagram. We have a uniform electric field which is represented by the green lines. These lines are equally spaced from each other, so which represent a uniform where at every point electric field is constant, and we will place a electric dipole inside this electric field, inside this uniform electric field. Let us consider this dipole is making angle theta with the electric field. Minus q and plus q are the charges on the electric dipole, and this p represent the direction of dipole moment in this diagram. Now when you will place a charged particle inside the electric field, that charged particle will experience a force. So this positive q charge will experience a force due to the electric field. So we know the direction of force due to the electric field on this positive q charge will be towards the direction of the electric field. So this is the direction of electric field, and that force will be F is equal to q E. Similarly, for negative q charge, as we know, the direction of force for negative charge is opposite to the direction of the electric field. The force will act on minus q charge will be opposite, and because the charges are same but their sign are opposite, so because of that the force will also same but opposite in directions. So what does it mean? It means there will be no net torque or net force acting on the dipole. So first case is because both forces are equal and opposite, it means there is no net force acting on the dipole. But we have negative q charge and positive q charge, and we place this system at angle theta. So what will happen? Because here if you see the force acting at two different points and both are equal and opposite, so these two forces try to rotate the dipole. So there will be no linear motion, translational motion will be not there, translational motion will not be there, no translation motion, no translation motion because both forces are equal and opposite. So because net force is 0, net force is equal to 0 in this case, but these two forces are acting on different point and both are equal and opposite. So these two forces acting at different point, they will try to rotate the dipole, they will try to rotate the dipole. So linear motion is not there, translation motion is not there. What kind of motion will be there? Rotational motion will be there, and we know for rotational motion we need to calculate the torque. So now we will calculate the torque acting on this dipole. So let's start. Let us consider this distance. The perpendicular distance of dipole is this AC distance. This is your perpendicular distance of dipole. So we'll take this one as A point, and this one as B point, and this one as C point. So now we will find the net torque. So as we know, the net torque is equal to force, either force and the perpendicular distance. So force into perpendicular distance from the axis of rotation. So this is your axis of rotation, and from this distance is your AC. So we need to find this distance. So we will find distance AC. So if you can find this distance AC by using this triangle ABC. So in triangle ABC you need to find sine theta. So what is sine theta? That is perpendicular, that is your AC and AB. So AC will be equal to AB sine theta. And what is AC? You can see the diagram. AC is the thing which we need to find, that is the perpendicular distance. And what is AB? AB is your 2L. So we will substitute the value of AB. AB is equal to 2L sine theta. So this is the perpendicular distance. And what is torque? Force into perpendicular distance, that is 2L sine theta. And we know what is force. Force is Q into E, 2L sine theta. And we know dipole moment P is equal to 2A, product of the either charge and distance. So here we can write 2L. 2L is the length. So 2L and Q is equal to P. PE sine theta. This is the expression. That much torque is acting on the dipole, with which the dipole will start rotation. And we can write it in the vector form, that is P cross E. So this is the expression for torque. When we will place a dipole inside the electric field, it will experience a torque. That torque is equal to P cross E. Okay. Now we will discuss. You can read this thing. The force of magnitude QE and this QE opposite to each other, and hence net force acting on the dipole due to external uniform electric field is 0. There is no translation motion of the dipole. However, the forces are along different line of action. These two forces are acting on different line of action and constitute a couple. So they will experience a torque. So torque is equal to electric force into perpendicular distance. So you will get torque is equal to P cross E, and you can find the direction of torque using screw rule. So the direction of torque is perpendicular to P and E. Now special case we will discuss one by one. The first thing is stable equilibrium. So when stable equilibrium is there, when the direction of electric field lines and dipole moment direction and the electric field direction both are same side, so angle theta will be equal to 0. So torque is equal to P sine theta. If you substitute theta is 0, sine 0 is equal to 0. So you will get torque is equal to 0. So in that case the torque is acting 0 and the dipole is in the stable equilibrium. That is very important point. Now next, unstable equilibrium. One is unstable equilibrium when the direction of electric field and the torque and the direction of dipole moment, when both are acting in the opposite direction. So this side, this is the direction of dipole moment P, and electric field this side. So both are forming 180-degree angle. So that time torque try to rotate the electric dipole so that it can change its direction by 180-degree and come to the stable position. So because of that it is known as unstable equilibrium, because torque try to rotate the dipole from this side to this side so that both electric field and dipole moment attain the same direction. So that's why we call theta is equal to 1 degree as a unstable equilibrium. Now the next one is when theta is 90 degrees. So we know sine 90 is equal to 1. So that time your torque is maximum. So these three are the special case for the torque. Now we will discuss another topic. The name of the topic is potential energy of a dipole in a uniform electric field. So now in this case we have a uniform electric field, and let us consider one dipole is there, minus q, positive q, and this dipole is making angle, it is making angle theta 1. Okay, now suppose we rotated this dipole by angle theta 2. We want to rotate, so what we will do, we will rotate this dipole in clockwise direction. So let us, the new position of dipole is, let us, this one is the new position of dipole. So I will draw with a different color so that it can appear properly. So let us consider this is the new position of dipole. Okay, I will rotate it anti-clockwise. Any direction you can take, it will be easy to draw me here. So that's why I rotate by this. So now I rotated it as anti-clockwise direction. Minus q will be here and plus q is there, and now it is making angle theta 2 with the electric field line. Okay, earlier it was making theta 1, now it is making theta 2 angle. So when I have rotated this dipole from theta 1 to theta 2, so that time I need to do some work. So that work firstly we will calculate, and that work will be stored as a potential energy. So firstly we will find the work done. So we have rotated here this dipole from theta 1 to theta 2. So let us consider, we will take a intermediate position where minus q, positive q is there. So let us consider it is rotated by angle d theta. So that time we need to do work. So let us consider when we rotate by theta angle a dipole, so that time we need to find the work done. So during rotation we will use this formula, torque into angular displacement. So what is the torque formula? We will use here, torque is PE and sine theta. Torque we know, PE sine theta, this is d theta. This is a small amount of work done, but actually we have rotated it from theta 1 to theta 2. So we have to find the work done for theta 1 to theta 2. So total work done will be from theta 1 to theta 2 PE sine theta d theta. So now we will integrate it and we'll find the work done. We know P is constant because dipole moment is not changing, charge is not changing, even displacement is not changing. So dipole moment will be constant, electric field will also constant. So we will left with only sine theta d theta, and now we will integrate it. We know the integration of sine theta is minus cos theta, and you will get the powers. We can take minus outside from this braces, theta 2 theta 1. In next step substitute the power. So how will you substitute? First one upper limit, then minus sign, then subtract lower limit. Okay, so this is the final expression for work done, and this work done stored as a potential energy in the dipole. This work done is due to the position of the dipole. Firstly it was at theta 1, second time it was at theta 2 position. So that time this is the potential energy stored in the dipole. Now we will discuss some particular cases. So let's start some special cases. When theta is equal to 0 and in this case when theta 1 is 0, let theta 1 is 0 and theta 2 is theta. So what will happen? So if you substitute this condition here, W is equal to minus P cos theta is cos theta 2 is cos theta, you replace cos theta, and cos theta 1 is your cos 0. So in that case what will you get? W is equal to minus PE cos theta. It means initially your dipole and electric field both are in the same direction. So when both are in the same direction, theta 1 is 0, and when you will rotate your dipole by some angle, that is your theta 2. So we don't know how much angle we will use to rotate it, so that's why we will take here general term theta. So in that way you will get W is equal to minus PE cos theta when initially electric dipole and the electric field have the same direction. Now the second case, when the direction of electric field and the dipole making initially angle 90 degree. So in that case initially it is 90 degree and now you will rotate the dipole. So that time suppose angle is theta. So now substitute the values by placing inside this equation. Cos 90 is 0. So you will get minus PE cos theta. So that time this is the potential energy stored in the dipole. So now we discuss here two cases when potential energy, when your dipole is at 90 degree initially and then turn by some angle. So in that case this is your potential energy stored in it. And when dipole is initially at rest, it is making angle theta, both P and E are making the same angle, that is theta is equal to 0, both are aligning at the same direction. So in that case this is the work done and the energy stored, and this is the final expression. Okay, so today we have completed these two topics, and next time we will do one more topic from this chapter. The name of the topic is electric field intensity at any point on the axis of a uniformly charged ring. Till then, take care.